Shared work problems. Two pumps are submerged in the same water tank. Working together, the two pumps can empty the tank in 8 hours. That tells us that working together, the time to complete the job is 8 hours, so I'm going to put 8 in that entry. Working alone, the larger pump can empty the tank in 5 hours less time than the smaller pump. We have to be careful with this information. This doesn't give us the exact time for either pump, but rather tells us how they are related. This means that if the small pump requires X hours to complete the job, the large pump would require 5 hours less time, which comes out to be X minus 5. The fraction completed in 1 hour is kind of like thinking of it as a rate in jobs per hour. So if it takes 8 hours for the two pumps to complete the job together, it makes sense that in 1 hour, the two pumps together would complete 1/8 of the job. Following the same logic for the small pump and the large pump, even though our intuition doesn't help us as much with these, we can follow the same model to say, okay, for the small pump it must be 1 over x, and for the large pump it must be 1 over x minus 5. The way we get our equation is by looking at what gets done in 1 hour. In 1 hour, if both pumps are working together, the amount that the large pump completes, which is 1 over x minus 5, plus the amount that the small pump completes, which is 1 over x, is equal to the amount that the two pumps would complete working together, which is 1 over 8. So the equation this gives us is fairly simple to come up with, but as we will see, it doesn't stay all that simple in the process of solving. This is a rational equation, so we need to find the LCD. None of these denominators have any common factors, so my LCD has all of the factors from the denominators. And I am going to multiply both sides of this equation by the LCD. 8x x minus 5, 8x x minus 5. We want to be careful when doing something like this that we distribute this LCD into both terms. We shouldn't cancel out with pen, because whatever cancels from our first product doesn't necessarily cancel from our second product. However, over here on the right-hand side, because I'm only multiplying by one term, I can go ahead and cancel with pen to clearly see what remains after canceling common factors. Alright, so working just with the equation now. From my first term, the x minus 5's would cancel, and I would have just 8x from my LCD times 1 from my numerator. In my second term, the x factors would cancel, and I would have just 8 from my LCD and x minus 5 from my LCD remaining. On the right-hand side, as I saw, just the 8 factor canceled, so I still have x and x minus 5 from my LCD. What I'm going to do now is start distributing and see what kind of equation I have to work with. (8x) plus 8x minus 40 equals x squared minus 5x. Combining like terms on the left, I get 16x minus 40 equals x squared minus 5x. Because it looks like I have a quadratic equation here, I'm going to want to get all terms on the same side. So I will subtract 16x from both sides, and I will add 40 to both sides. I'm choosing to move these terms over to the right rather than the left because that will give me a positive leading coefficient. So my equation is now 0 equals x squared minus 21x plus 40. Anytime that we are solving a quadratic equation, it probably makes sense to give a little bit of time to attempting to factor the equation or attempting to factor the polynomial. But if we give up on factoring this one, we would then resort to the quadratic formula. So our next step is to plug in a, b, and c into the quadratic formula and start to focus on simplifying our answer to find a value of x. All over 2a. So after plugging into the quadratic formula and simplifying things a little bit, I'm down to 21 plus or minus the square root of 281 over 2. Since this is an application and 281 is not a perfect square, we're going to get a decimal approximation here. A simplified radical answer isn't really that appropriate here because what we're looking for is a number of hours that we can understand. So to get a decimal approximation, I'm going to have to break apart that plus or minus and now write it as two separate expressions, 21 plus the square root of 281 over 2, and 21 minus the square root of 281 over 2. The best thing to do in getting a decimal approximation here is to let your calculator store all of the values. I'm not going to punch in square root of 281 and write that down somewhere and then get ready to plug it back in, because chances are if I do that, I'm going to round it off a little bit too much. So to enter this into my calculator, the first thing that I need to do is think about the implied parentheses here. The whole numerator needs to be in parentheses for your calculator to know that that whole numerator is divided by 2 instead of just the last term that you entered. Some calculators might also put an open parenthesis automatically as soon as you type in your square root, so you may need another closed parenthesis around your radicand, your 281. That's going to depend a little bit on your calculator. This calculator will not require me to do that. I'm going to start with an open parenthesis, 21 plus 281 square root. In this case, this calculator takes the square root of whatever number shows on the screen when I click it, close parenthesis, then divided by 2 to get 18.88. I'm going to round that off to 18.9 for the sake of this calculation. Now I'll go ahead and put the other one in. Open parenthesis, 21 minus, I'm going to enter the 281 and then the square root button because that's the way this calculator works. Close parenthesis, divided by 2 equals 2.118. I'm going to round that off to 2.1 for the sake of this calculation. Now I need to figure out whether both of these are reasonable answers. And again, remember that these are values of x, so we need to go back to our original variable definition to see what x means. In this table here, I can see that x is the time to complete the job for the small pump, and x minus 5 is the time to complete the job for the large pump. This tells me that my answer 2.1 isn't really reasonable because it makes x minus 5, the time for the large pump, negative. So I'm just going to keep the answer 18.9. X is 18.9, that's the time for the small pump. So the small pump requires 18.9 hours. And the large pump is going to be X minus 5. So I'll find 18.9 minus 5, which is 13.9. So that's going to be 13.9 hours for the larger pump. It's always a good idea to look at these answers and make sure they seem reasonable. I would say that these answers do seem reasonable because the two of them working together would complete the job in 8 hours. So it is true that they would get the job done faster working together. And it's also true that if they were both exactly the same, you would expect each to take 16 hours. But they're not exactly the same, so one of them takes a little bit longer than 16 hours, and one of them takes a little bit less time than 16 hours. So this is a perfectly reasonable answer.